After running the PureTuring machine for 60 hours, this is as far as we got. This is a breadboard build, so I know it's not going to clock that fast. The clock period is just under 4 microseconds, which means it's clocking at about 250 kilohertz. The clock itself is very asymmetric, and I think it's got something to do with this. I perform an AND on a variable that's declared to be a long, immediately after raising the clock. Then a bit later, I either add one or subtract one from this variable as well. With a bit of work, I think I could shorten this period, but that'll only improve it by a factor of 2 or 3. When I tried to reduce this clock low period, the circuit would end up in an error state after an hour or so. The Apple II, with a 1 MHz processor, can get this far through Pacman in a fraction of a second. So let's have a look at the Apple II in a bit more detail. It has a 6502 microprocessor and 2 lots of memory, 48K of RAM and about 12K of ROM. The 6502 exchanges information with the external memory through the address bus and the data bus. It also has a separate read-write line that tells whether we want to write information to the memory or read information from the memory. Here we can see a write occurring to address 4, and we see a blue duck overriding the black duck that was there. Somehow in our Turing machine, we need to emulate all of this. These are the registers that are visible to the programmer in the 6502, and we should be able to identify all of these on the diagram. Here's the accumulator, index X and index Y, the program counter, stack pointer, and status register. But when we look closely, we can see a number of hidden registers, such as the memory address registers, the memory data register. There's an A register, B register, and hold register around the ALU. There are some other registers that look like they're used for calculating effective address. And we also have an instruction register and a pre-decode register. None of these registers are visible to the user, but they're required for operation. So in our code, I'm going to need to model most, if not all of these. I'll start with the user visible view of the registers and add the hidden registers 1 or 2 at a time. We have a B register which feeds the ALU, and I think it's hidden from the programming model because there's no guarantee of consistency between instructions. The 6502 has an A register and an accumulator, but I've just merged them into a single register that I call A. Next, we have a data output register for writing to memory. We also have a memory address high and a memory address low register. I'll add these to our model, and they're all presumed to be 8 bits each. I need an 8-bit instruction register, and I've also added an 8-bit micro-instruction register. I'll show how I use these together in a later video. These 2 registers, program counter high select and program counter low select, I'm going to add as effective address register A. This is also made of a high and a low register. I'm also going to add a second effective address register, effective address B, which I think I'm going to need for the complex addressing modes. Finally, I'm going to add a U and a V register, which just shadow the index X and index Y register. I'll try to design these out later. We've already seen the status register and the A and B registers interleaved in a previous video, and I showed that the interleaving makes it easier to perform operations between these 2 registers. Next, I want to add in the program counter and the effective address registers. I'm going to group PC high, effective address A high, and effective address B high, and lay them out in an interleave fashion on the notepad next. I do the same for PC low, effective address A, and effective address B low. Next, I'm going to put down the instruction register and the micro instruction register, but this time I'm going to leave a double dollar between the 2 of them. At the end of every micro instruction, I need to go back to this point, and the double dollar just makes it easier to find. Next, we lay down the stack pointer. That's pretty straightforward. Now for the index registers and their shadow registers. They go down on the notepad next. Now I want to lay down the interface between these main registers and the memory system. So I'm going to need to make some space for the D register, for memory address low and memory address high. I'm going to use another $double here to delineate these. If you remember back to a previous video, I snooped on the notepad from location 141, 150, and 159 to check for a write to main memory. This is how I was able to display the pixel stream. Now that I've made space for all these registers on the notepad, how do I build a memory system? The first thing I'm going to do is use 3 consecutive dollar symbols to separate the CPU registers from the main memory. Next, I just lay down each memory byte one at a time. I put a dollar symbol between them, so this means each byte occupies 9 notepad locations. Main memory byte 0 first, then main memory byte 1, main memory byte 2, and I think you get the picture. On top of this, I arrange each group of 256 bytes into a page, and I put an extra dollar symbol between each page. So there are 256 pages of 256 bytes. Now, one of the things I hope you've noticed is that there should be no underscores in the memory system. There are zeros and ones to represent the data, and there are various number of dollar symbols to delineate the regions. So how do I access a single byte within this vast region of zeros, ones, and dollars? You guessed it, I use the underscore. MAR high contains the page that I'm interested in. I go to the start and mark it with an underscore. This page contains the byte that I'm interested in. So I want to skip over all the pages before it and mark the start of the next page with an underscore. Going back to the MAR, we change the leading dollar into an underscore. Next, I read the most significant bit of the MAR high register and then branch based on the value found. I move to the next bit and then generate another set of branches. Then I keep doing this, forming a tree until I'm right down to the last bit. The rule number, or state, now tells me exactly which page I need to access. And I'll have used all the bits in MAR high. To make things simple, let's just say I have 4 pages. This means I have 2 bits in my MAR high. For each possibility, I need to step over the dollar symbol at the start of the memory system. Then for page 0, I need to step over the next 2 dollar symbols and convert the third dollar symbol into an underscore. This marks page 0 as the page I'm interested in. Now for page 1, I want to step over the first double dollar, then step over all the zeros and ones in between. And then when I find a double dollar, I want to change the second dollar into an underscore. This marks page 1 as the page that I'm interested in. Then for page 2, first I skip over page 0, then I skip over page 1, and I mark the start of page 2. Similarly for page 3, I need to skip over pages 0, 1 and 2 and mark the start of page 3. This little animation may help. Let's assume that we're interested in page 3. We pass the first dollar, we pass the second dollar symbol, then when we hit the third dollar, we move up a level. Here we skip over the bits one at a time. Eventually we'll hit a byte marker, but if we don't see a page boundary, we just go back to skipping over bits. Once we get here, we've skipped over page 0, and now we start skipping over the contents of page 1. We keep going right until we find another double dollar symbol, which marks the end of page 1. Then we go up to the next level, which is the start of page 2. We go through the whole process, skipping over page 2. But this time, when we hit the double dollar, we'll actually be at the start of page 3, which is where we want to be. We mark it with an underscore. But now we want to scoot left all the way back to the start of MAR high and change the underscore to a dollar. We do that by moving left here continuously until we find the underscore at the start of MAR high. We change it to a dollar and then we're done. Now that we've found the page that we're interested in, we want to mark the byte. We go back and read the value in MAR low. Then we want to move the underscore at the start of the page to the actual byte that we're interested in. We read MAR low and form this tree structure just as we did for MAR high, but this time the rule number represents the byte position rather than the page position. If we're interested in byte 0, then we don't actually need to do anything because the underscore is already where we want it. We just need to remove the underscore at the start of MAR low. For byte 1, we skip right until we find an underscore symbol. We exchange the underscore for $1. Then we skip over all the bits in byte 0. When we find the next $, this marks the start of byte 1 within the page, and so we mark it with an underscore. And then go all the way back to the start and remove the underscore in front of MAR low. If we're interested in byte 2, then we need to skip over bytes 0 and byte 1. And for byte 3, we need to skip over bytes 0, 1 and 2. Let's say we're interested in byte 3 this time. We keep moving right until we find the underscore marking the start of the page. We change this to $1, then skip over byte 0. When we find another $, we go up to the next level and skip byte 1. We do this again to skip byte 2, and then when we found $1 at the start of byte 3, we mark it with an underscore, then go back all the way to the beginning of MAR low and change the underscore back to $1. By this stage, the $, in front of the byte that we're interested in has been changed to an underscore so it's easy to find. Let's say we want to do a write this operation, so the value in the D register should go into the main memory. We skip through the data register, forming an encode tree. This time, the rule number encodes the value of the data we want to write. Once we've done that, we skip to the start of our byte in main memory, and we do that by searching for the underscore symbol. Once we've found it, we replace it with $, then we start laying down bits in that byte location using the decode tree. One of the problems with the way I've drawn the decode tree is it'll actually lay down the bit pattern in reverse order. We can correct this, but our decode tree is a bit messier. Let's say we want to write the value 3. We keep going right until we find our underscore symbol, and once we have, we replace it with $. Next, we go down the decode tree and write the value 3 into that byte location. We keep going left until we get back to the start of the data register, which we previously marked with an underscore, and change the underscore back to $1. So why is memory access so slow? Well, first we have to go all the way out and mark the page number, then come back. Next, we go out and mark the byte number within a page, and then come back. And then finally, we have to go out again, read or write the data we're interested in, and come back. So we've had to make 3 round trips that could be the entire length of the tape. We have $1 at the start of each byte and another $1 at the start of each page. That means that each page requires 2,305 symbols. Our notepad's 512K, but we have 172 bytes at the start for our registers. That means on this machine we only have 227 pages rather than 256. This means we can only go up to E361. For Pacman, I don't start using the reset vectors at FFFC and FFFD, I jump straight into 7AF5. Unfortunately, Pacman doesn't use any addresses above D1000. Let's say 7AF5 is about halfway through our tape. It's going to take 250,000 clocks to get out there, and 500,000 for a return trip. We need 3 return trips to do the read, so that's about 1.5 million clocks. On the emulator, I kept track of the amount of time we spend in the register region, which is below 172, and the amount of time we spent in the memory region. And it turns out we spend 90 to 99% of our time just doing the main memory reads and writes. And this is the real message for this video. Sequential memories are really slow, and they're the Achilles heel of a pure Turing machine. I think this is one of the main reasons we don't use the machine the way Turing originally envisaged. What I'm going to do in the next video is divide the tape into 2 different memory systems, and hopefully in memory system B we'll be able to use some of the random access that's available in the static RAM. But that's it for now, so don't forget, like, share and subscribe.